Hey, today we're going to talk about barometric pressure or air pressure, as you probably more commonly refer to it. Air pressure on Earth is caused by the weight of the atmosphere pushing in on us. Sometimes you'll hear it said as the weight pushing down on us, but it's kind of like swimming in a swimming pool. If you go to the deep end of a swimming pool and you swim to the bottom of the pool, you feel the pressure pushing inward, especially on your ears. A lot of times it'll hurt people's ears if they go too deep in the water. And that's 10 feet of water, which it turns out weighs quite a bit more than the atmosphere. The atmosphere weighs about 15 pounds per square inch, and that weight is pushing inward on us and kind of squeezing us together. If you were going to instantly teleport out into space on a cellular level, each individual cell would probably just explode because there's 15 pounds of pressure pushing outward on each cell. And if you just teleported into space, all of a sudden there's no pressure holding the cell together and it would just pop apart. Of course, your lungs would explode and all that. It'd be great. It'd kind of messy, though. Don't try it. In the United States, we measure pressure in inches of mercury. That's the English unit. And the standard atmospheric pressure at sea level on the planet Earth is 29.92 inches of mercury. Now, I'll explain what that name means a little bit later when we talk about instruments. I'll explain why it's inches of mercury. It's kind of a bizarre name for a unit. In the rest of the world, you'll probably see it measured in millibars or kilopascals. Now, millibars is the universal air pressure unit. Meteorologists in the United States use millibars frequently, and then they kind of have to go back and forth between inches of mercury and millibars. Fortunately for you, you have this awesome earth science reference table thing over here that's going to help you do that without having to do the math. But if you want to do the math, 1 inch of mercury is equal to 33.86 millibars. Now, the standard atmospheric pressure, if you wanted to do the math, the standard atmospheric pressure at sea level on Earth is 1,013.2 millibars. Now, in kind of a quirk, if you go to Canada, they will report the air pressure in kilopascals. So it would be 101.32 kilopascals. If you look at the millibar number and all the digits seem the same, it's because they are. They just move the decimal place one to the left. I don't know why they do that, but it's Canada, whatever. It's what they do. Okay, so let's talk about air pressure. But first, let's go back a lesson and talk about temperature. Temperature is the average kinetic energy of the molecules, or how fast they're moving. So the higher the temperature, the faster the molecules are moving. So when it's warm outside, the molecules move quickly, and they'll spread out because in the Earth's atmosphere there's nothing to contain them. So they'll just spread out. That makes the air less dense. So when we think of warm air, we can think of low density air. When it's cold, the molecules aren't moving as quickly. They tend to pack more tightly together, and that's going to be high density air. Warmer temperatures, which equal low density air, equal low pressure air, because again, the pressure pushing in on you is directly related to the density of the air around you. So warmer temperatures equal lower pressure. Cooler temperatures equal higher pressure. Now, back to that inches of mercury thing. The very first instrument used to measure air pressure was something called a barometer. Now, again, the other day in the lesson on temperature, we talked about the thermometer and its invention by Galileo and how he kind of ripped off someone else, and this is it. If we look at the barometer, it's a test tube filled with mercury, and it's flipped upside down and placed in a dish of mercury, an open dish of mercury. The little gas bubble up here isn't gas at all. It's a vacuum. I did a demo in class, and I kind of tried to explain that that should be a vacuum, but I didn't have a way of making it a vacuum. So Torricelli in 1640 invented the air pressure barometer. And the way it works, as the air pressure or density outside increases, it's going to push down on the mercury in the dish. And the only place the mercury has to go is up the tube. The only way this is different from a thermometer is a thermometer had a lid on this dish which sealed it off and prevented the air pressure from affecting it, so that only the expansion and contraction of the mercury had any, due to temperature, had any effect on the height of the liquid in the tube. So a barometer is based solely on pressure pushing downward on the liquid in the dish. A thermometer is based solely on the expansion and contraction of the liquid in the dish. Now, Pascal, who was a person, a scientist around at the same time, who knew Torricelli, he and Torricelli worked pretty extensively with this barometer. One of the first things they did was they climbed up a mountain with it, and they discovered that air pressure did in fact decrease as you go higher in Earth's atmosphere. In other words, if there's less air above you, the air is less dense, there's less pressure pushing inward. The next thing they noticed was just leaving it out on the table day after day after day, they noticed that the height varied from day to day. They had discovered air pressure. Okay, just as a little aside, I want you to watch this little video, and I want you to write down on the side of your paper why this little cloud of vapor is occurring around the airplane. Now, let me be clear. This is not an airplane breaking sound. It's an airplane flying actually fairly slow over the ocean. Now, it could be, and you can watch any number of these videos right here. It could be breaking the sound barrier. That's irrelevant, except it's not. Some of these videos that say sonic boom really are. Some of them aren't. A sonic boom sounds like an explosion, and when a plane comes over going slow, it can sound like an explosion. So some of these, like over here, it's a sonic boom, maybe it's a sonic boom. It depends. Some of them really are. Some of them really aren't. Let's go back to where we were. So what I want you to do in your notes, I want you to just hypothesize what is causing the water vapor to condense right here around the outside of the plane and a little bit right here behind the cockpit. Finally, we're talking about air pressure. This is a weather map. It's a synoptic weather map. The L's represent low pressure. The H's represent high pressure areas on the surface of the Earth. And sometimes they can even be aloft, but we'll talk about that later. What I want you to do, another thing I want you to write on your paper, I want you to tell me what generally you feel like the weather would be around a low pressure, and generally what you think the weather is like around high pressure. So we've got one down here in Florida, one here in Central California. We've got a low in Central Montana, one in Nebraska, and then one off the coast that we really can't see.